All right, this is the first area and volumes AP packet that we're going to work on. I'm not sure how many problems I'll get through in the time that I have left this morning, so we'll just see how far we get. This first AP problem we're allowed to use a calculator on. So this says an oil storage tank has the shape shown above, obtained by revolving the curve y equals 9 over 625 times x to the fourth from 0 to 5 about the y-axis, where x and y are measured in feet. And you're rotating it about the y-axis. So that tells me that I should be probably solving this equation for x instead of y. Oil flows into the tank at a constant rate of 9 cubic feet per minute. So it says cubic feet per minute. So that's a dV dt. And because we're filling the tank, it's equal to positive 8 cubic feet per minute. So I'm just going to note that for myself. Find the volume of the tank, indicate the units of measure. All right, so the volume of the tank is going to be we're rotating around the y-axis here, right? So it's going to be the integral of r squared times pi when we do right minus left. So let's get this equation solved. So instead of y equals 9 over 625 times x squared, let's solve this for x. So multiply by 625 over 9 times y, and then square root that. Like this. I'm going to put the y up here so it doesn't look so weird. And technically there's a plus or minus there, but again, the original x values are here and you're rotating it around, so those are going to be positive. So find the volume. So r is equal to the square root of 625 y over 9 minus 0. So the volume is pi times the integral from we don't want the x value 0 to 5. We want to know what the y values are. Now, you don't have to do any math here. What's the bottom? 0. What's the top? It shows you here 9 feet. So from 0 to 9 of r squared. So when you square the square root, you're going to get rid of the square root, dy. Now, I'm using a calculator, so I'm not going to worry about rewriting that. So pi times the integral from 0 to 9 of, I'm not going to type in the square root here though, so 625x over 9 dx. So my answer is 8,835.729. Let me just confirm that with my first one because that answer doesn't sound familiar. Oh, what happened? Oh, it's a fourth root. What? Fourth root. Okay, to the fourth. It's not squared. That makes this a fourth root. That makes this a fourth root. When I square it, that makes this a square root. Let me try that again. Unfortunately, I can't insert a square root in here, so I'm just going to delete what I have. Okay, so square root of 625x over 9. That's better. I thought that sounded like an unfamiliar number. So what was it? 471.239. What are the units? Indicate units of measure. Volume, they told us, was cubic feet. All right. Part B, to the nearest minute, how long would it take to fill the tank if the tank was empty initially? So this is not calculus. This is saying we know that the tank is being filled at 8 cubic feet per minute, and we've got 471 cubic feet to fill. So it's going to be 8 times t is equal to 471.239. And we just solve for t. Now, don't use your rounded version. You still have this on your calculator and just divide it by 8. So 58.905. I should have approximations here. What's the time on that? This was feet per minute, so that's how many minutes it would take. Okay, and then part C, let H be the depth in feet. So H is really just, instead of Y, they're having this be H. So for part C, okay, H is Y, really. How fast is the depth of the oil in the tank increasing when H is 4? Indicate units of measure. So how fast is something? So they want us to find dH dt. So this feels like a related rates. What do we know? We know dV dt is 8 cubic feet per minute. They want us to find dH dt when H equals 4. And what are we going to use? Well, we do have this volume equation, right? We have that volume is equal to pi times the integral from 0, time is 0, to some time, just some other time. And then when I squared the fourth root, excuse me, when I squared the fourth root, that left me with a square root of 625. And then just instead of y, oh no, wait, sorry. We're not going 0 to t. We're going 0 to h. There we go. Going 0 to h. The reason they gave us the h instead of the y is because we're going from a height of 0 to a height of h. The oil is filled anywhere between the bottom and the top. And we can still have y in here temporarily. Because what are we going to do with this? I want to find how fast the depth of the oil. I want to find a dH dt. So I should take the derivative with respect to t of both sides. So if this is dV dt, when I take the derivative of the integral, remember that cancels out. This is that second fundamental theorem. And the h goes into the function for the y. So this is going to be pi times the square root of 625h over 9. And then here's the other thing. Remember, because this is h and this is not a t, we're taking derivative with respect to t, we have to chain rule that says times dH dt. So that's where that comes into play. I have a number for dV dt. It's 8. They told me to find dH dt when h was 4, so now I have that. Put that in for h. And solve this for dH dt. So now things can be simplified, right? What's the square root of 625? Is that 25? I should probably know that. Yeah, that's 25. So really this is like 25 times 2. So this is 50 over 3, if I square root that, times pi, equals 8 times dH dt. Okay, so we can say, all right, multiply by 3. So 3 over 50 pi times 8. Reduce 8 and 50 by 2. So I'm getting 12 over 25 pi. You could also, this is feet per minute. You could also, you have a calculator, you could get the decimal version of that. All right, I think I have time for one more problem. So let's do number 2. Number 2 is a non-calculator. Let me double check that. Yeah, number 2 is a no calculator problem. So sketch the graph of f. F of x is the square root function. Shade the region R enclosed by the graph of f, the x-axis, and the vertical line x equals 6. So part A is just sketch this thing. So the square root of x graph has been shifted to the right 3 units. So instead of starting at 0, 0, it starts at 3, 0. Typically goes off to the right. Get my pen working again. Goes off this way. We're supposed to stop at 6. And if you plug in 6 to this, you get a height of radical 3. Shade the region R. So that's this region here. All right. And then for part B, it says find the area of R described in part A. So I'm going to go top minus bottom. And this is the integral from 3 to 6 of the square root of x minus 3 dx. This is just area, not volume. So there's no pi, there's no squaring things. All right, so this is sort of a little mini u sub, although u sub doesn't matter here because u is x minus 3, du dx is 1. So there's no adjustment I need to make. It's just the integral from 3 to 6 of square root of u du. So when you add 1 to that exponent, you get x minus 3 to the 3 halves over 3 halves. And you're plugging in 3 to 6. All right, so start with plugging in 6. You get 2 thirds times 3 to the 3 halves. Minus plug in 3, you get 2 thirds times 0 to 3 halves. So, okay. And then when we simplify this, 2 times 3 halves, I can subtract exponents here. 3 halves minus 1 is 2 times 3 to the 1 half, or 2 times radical 3. So that's the area there. Part C says rather than using the line x equals 6 in part A, consider the line x equals w, so that can be anywhere, where w can be any number to the right of 3. Let A of w be the area of the region enclosed by the graph of f, the x-axis, and the vertical line. Write an integral expression for A of w. It should be the same setup you had for part B, with the exception that instead of going from 3 to 6, we're going from 3 to w. But otherwise, we keep the same thing. Remember, the variable inside of the integral just has to be different than what you have up here. So you can keep this as x. And yeah, there's nothing else to do with that. And then for part D, let A of w be as described in part C. Find the rate of change of A with respect to w when w is 6. So right now it's A of w. So find dA dw. Okay, take the derivative of both sides. Now this one's interesting because you're taking the derivative of the integral, which cancels out. You're plugging the w into here. So you get square root of w minus 3. And then normally we say, oh, but don't forget your dw dt. Well, in this case, it's like, don't forget your dw dw, right? You're taking the derivative with respect to w. So that is just 1. So that does not need to be there. So it's just dA dw is equal to square root of w minus 3. All right, I'm going to stop this video here, and then the next video will have the next couple of problems when I have more time to work on them.